So we're going to start with an example that will help us figure some more things out about that equation that describes motion. So we're going to start with page 436, number 9. If somebody would read it for us, please. This is 1036. Okay, so we got to find a whole bunch of stuff. So this is our equation here. And the general equation that goes with this, remember, is xm is cosine omega t plus v, which may help us figure out what some of the things are that we need to find. So we're supposed to be doing everything for t is equal to 2 seconds. And what does part A ask us to find? Okay, so that's really asking me to use my x equation. And so we're just going to substitute in. So my 6 meters stays the same. I'm going to have the cosine of 3 pi times 2 plus pi over 3. Well, you're going to take the cosine of it. Okay, so this is going to give me 6 pi plus pi over 3. And of course, the 6 pi, that just means I've gone all the way around 3 times. So I can kind of ignore that. So what's the cosine of pi over 3? Make sure you're in radian mode. Okay, I think that's about right. So what's the position going to be at 2 seconds? Yeah, 3.0 meters. Okay. So that's pretty straightforward. What does part B ask us to find? So if we have to find the velocity, how do we find that? What is velocity always equal to? dx dt. Okay, so I'm going to take d by dt of 6.0 times the cosine 3 pi t plus pi over 3, right? Did I copy it right? Or remember it right? So my 6 is just going to hang out front because it's just a constant, right? And what's the derivative of cosine? Negative sine. So it's going to be negative sine 3 pi t plus pi over 3. But then what do I have to do? I have to take the derivative of what's inside, which is going to give me 3 pi. So there's a lot of factors running around here, so I would rather rewrite it. So this is going to give me negative 18 pi, right? Because I've got my 6 and my 3 pi, times the sine of 3 pi t plus pi over 3. I could, but I think what we're really going to find is that if t is equal to 2 for all of these, because it's the problem reads at t equals 2 seconds, what are all of these things? Okay, so we're really going to find v of 2 seconds. So that gives me negative 18 pi times the sine of 3 pi times 2 plus pi over 3. So what am I going to get? And you can leave it, I don't know. I guess I put it into a decimal. I substituted in for the pi. Okay. And the units really are meters per second. Remember that the units for the 3 pi were really radians per second. Remember that the units for that 6 out front were really meters. You shouldn't have. Are you in radian mode? You gotta be in radian mode. Well, because, hang on. It said back here that the units inside that cosine were radians. Okay, so that means that when you take the cosine of whatever that angle is going to be, you need to be in radian mode on your calculator. Okay, did that answer your question, Sari? Okay, I couldn't hear because Casey was talking. All right, so you need to be in radian mode. I don't know why you're wrong. You should get, it's the sine of 60. You should get radical 3 over 2. So make sure that when you take the cosine of pi over 3, you should be getting 0.866. And then you're just multiplying it by 18 and multiplying it by pi. But that is the right answer. Okay. How about part C? What does part C want us to find? The acceleration. How do I always find acceleration? Yeah, so dv dt. So I'm going to take the derivative of, what is it, negative 18 pi sine 3 pi t plus pi over 3. So I have to take the derivative. Again, my negative 18 pi can just kind of hang out there. What's the derivative of sine? Cosine. But am I done? I have to take the derivative of what's inside, which is what? 3 pi. So again, I got a lot of stuff hanging out here. So I'm just going to rewrite this. A of t is going to give me negative 54 pi squared cosine 3 pi t plus pi over 3. And of course, what the problem is really asking me for is what that acceleration is at 2 seconds. And effectively, I'm just taking the cosine of pi over 3, which Gianni already told us was a half. So Priya, what'd you get? What?
Oh, never mind. I forgot to multiply by
Pi squared? What'd you get, Sari? No. Okay, well, it should be negative. And we've only got 2 sig figs. So let's round that. And remember, this is acceleration, so it's meters per second squared. And again, my 18 over here had units of meters per second. And when I took the derivative of what's inside, my 3 pi had units of radians per second. Okay, do we get that now? All right. Everybody's calculators behaving. Okay. All right, so how about part D? What does part D ask us to find? The phase. So that we can actually get right from our initial equation. What is the phase of the motion? Yeah, it's this whole thing right here. So 3 pi t plus pi over 3, and I'm going to substitute in t equals 2, right? Gives me what? So 20 what? What are my units? Well, just radians, actually. So that's going to give me 6 pi, which is about 18 and a bit, and pi over 3, which is about 1. So yeah, I think that probably is going to be 19. What is it? Oh, yeah. 19 pi over 3. Yeah, I would believe that. Did everybody else get that? We good? Okay, so how about part E? What are we supposed to find there? The frequency? Or, okay, so we're supposed to find the frequency. What's the symbol that goes with frequency? No, I want to know the letter that goes with frequency. No. F. What? Little f. But somebody brought up omega. What's omega equal to? Okay, I would take a variety of answers here. No, this is just omega. Okay, if we compare it back to our original general equation here, okay, the thing that's in front of the t is the omega. So we know that omega is going to be 3 pi radians per second. But how do I get from there to the frequency? Keeping in mind that okay, well, since there seems to be some question here, what does part F ask us to find? The period. And hang on, and what's my symbol for period? T. Okay, now, what else is omega? No, you got it. Okay, because remember that omega is also angular velocity. And if I assume that my velocity is a constant, which I can't always do, but we'll pretend, okay, then my angular velocity here means that I go all the way around, which is 2 pi, in one period, which is the time it takes me to make one complete trip. Okay, I like this formula because I think it makes a lot of sense. It's a good place to start. Okay, it's something you can figure out. It's something you can think about. So this tells you then that t is equal to what in terms of omega? Two pi over omega, right? Okay, the algebra's not that hard there. So that's going to give me 2 pi over 3 pi, or what's my answer going to be? Okay, so 0.67, and what are my units for period? Seconds. Okay. So now we have to go back and look at part E, which is to find the frequency. Now, you all took freshman physics with me or Mrs. Leas. So you should know, it should be in your head somewhere, a relationship between F and T. So how can I find F in terms of T? Yeah. If period is the amount of time it takes to do one cycle, and frequency is the number of cycles in one time, they have this inverse relationship. So that tells me that F is going to be 3 pi over 2 pi, or what? Thank you, Priya. And what are my units for frequency? But it has another name. What is it? You can give me letters. What's the letters? HC, which stands for Hertz. Okay. It's angular frequency. Okay, so if we back up here a little bit, and I've still got F is 1 over not pi. it's 1 over t, and t is equal to this. So this is 1 over 2 pi over omega, and a denominator of a denominator is a numerator. Okay, or even further, omega is 2 pi f. I've already circled that one. Okay, so there's a lot of different ways to get to what the answer might be. Okay. And since we're talking about omega, remember that we said that for a mass on a spring, omega is equal to k over m. Which means that the period is 2 pi square root m over k. All right? We good? Got it? Gianni, all right? Maybe? What don't you like? Because t is 2 pi over omega, so I have to flip it, flip the fraction. That's a good question. I was waiting for somebody to ask me about it. Okay? All right, so let's try it. I hesitate to say it, but I shall. A real problem. Okay? This one was just a plug and chug. Can you read things off of the equation? So let's try something that's a little harder. So let's try page 437, number 26. If somebody would read it for us, please.
And a spring decay constant are arranged on a horizontal frictionless surface. The coefficient of static friction between the two blocks is 0.4. Of simple harmonic motion on the square block system with its form block with the reduced slipping over.
Okay. So, draw my picture here. I have my big M. I have my little m. I have my spring of constant k. This surface down here is frictionless, but this surface has a mu that, what was it, 0.2, oh no, 0.4. Okay, my little m is 1.8 kilograms, and my big M is 10 kilograms. Okay. And so this is another one of those kind of extreme case problems where they say what amplitude of simple harmonic motion of the spring blocks system puts the smaller block on the verge of slipping over the larger block. So that means that I want to find the maximum amplitude so that those two things don't slip. Okay, so can you kind of picture this in your head? I've got my two blocks sitting on top of each other, and they're moving back and forth. Okay, and there's a friction force between them that keeps them from slipping over each other. There are tissues on my desk still. Oh, you're coughing. Do you really need water, Gianni? Oh, well, then let's turn the fan on. minute to, Okay, so now that we have the windows open and everybody's sitting in a place where their temperature is more comfortable. Okay. And remember, the key to SEM is layers that you can take off, because you'll be freezing when you get down to the atrium later, but it's just the way it's going to be. All right, so I hope you can picture it here. I've got one block on top of the other, and they're moving back and forth. Okay, and the trick is that I don't want the block on top to slip at all. So there's a friction force between them. And as long as the friction force, and what kind of friction force is it? Static or kinetic? Static, because it's between these two blocks that I don't want to move. Okay? As long as the maximum static friction force, because that's the only one I can calculate, is bigger than the restoring force, which means the force that the spring pulls on the block with, the top block won't slip. So as long as Fs max is, and of course we're going to say approximately equal to F spring, smaller block won't slip. Okay, and remember that this is between little m and big M. And this is what we call the restoring. Let me write that better. Between the spring and big M. Okay. And so we're going to find XM for that condition, that Fs max is equal to the force from the spring. It's coming. Well, because this is a mass on a spring, so this is going to be undergoing simple harmonic motion. It's just going to keep, the whole system is going to keep sliding back and forth, and I don't want the thing on top to slip off. Okay? All right, so what do you think I'm going to do first? No, we have not even talked about damped harmonic motion. Nothing to do with it. You're sitting in the AP exam. Your future depends on your ability to answer these questions. You got to write something down. What should you do? What should you write down? Free body diagrams. I got two forces, right? That's like what you do. When you have forces, you make free body diagrams for the objects. Okay? So we've got our little m. And our big M. So let's talk about little m first. What kind of forces do I have on little m? Okay. Now that's going to, the direction of static friction is going to depend on what? the direction of the motion. So we're going to make an assumption, because it makes my life easier, that the blocks move to the left. Okay. So what does that mean about the direction of the static friction force? What does the friction force do? What does the friction force always do? What does it always point in? Opposite the motion, or opposite the motion that the object would have if there was no friction. Yes, it's going to point this way. Now, if that static friction force is acting between little m and big M, it becomes a third law pair, so that it's also acting on the top of big M. Usually we think of the ground or the floor or the incline or whatever we have friction with isn't moving. But when both objects are moving, they're both experiencing that friction force. It's just a matter of where you're standing. Are you standing on this object, or are you standing on that object and looking at it? Okay. What other forces are going to be on M1? There's going to be a normal force. I'm going to call this the normal force from big N, because that's the thing it's sitting on. What else? Gravitational force. G little m. All right, how about big M? What else is going to be acting on big M? The normal from what? Okay, so there's going to be a normal. I'm going to say it's a table because I think it's resting on a table. Hang on, let Priya talk for a minute. No, because I've already kind of put that into here. But what else is going to act on this? Casey. Yeah, the normal force from little m. And those are going to be a third law pair. So I can say that those are equal in magnitude and opposite in direction. And what else am I going to have? The restoring force, okay? I'm going to have that force from the spring. And because it's moving to the left, it's pulling it that way. Yes, because it's only touching big M. It's the friction force that's bringing little m along with big M. Okay. But because we're assuming that this friction force exists, I can assume that big M and little m are moving as one thing. Okay. So now what do I do? Right, F net equals MA. I'm obligated to do that after I write my free body diagrams. Okay, that's why we have these algorithms for solving problems. Okay, so that you know what to do next. So I think if it's moving this way, I'm going to let that be positive x and up be positive y. Okay. So I'm kind of only at the moment worried about x. So I'm going to say that F net x is going to be little ma. And I've only got one force, right? And what's Fs max? Okay, which is going to be what? So this is going to give me mu little mg. You're going to give me ma. They will, but I'm not going to do that because I might not need that. It's the normal force from that block. But if you sum the forces in y in your head, you can see that that normal force has to be equal to the gravitational force on little m, which will be mg. So I'm going to do the same thing for big M. F naught x, now it's going to be big M times A. So I'm going to have F spring plus Fs max is going to be MA. So I'm going to have F spring minus Fs max in this situation is going to give me MA. Now remember that the magnitude of this Fs max and this Fs max are the same, because that friction force is always between the two objects that are rubbing each other, but it's a single force. It just points in opposite directions depending on which object we're talking about. So we could rewrite this as F spring minus MA gives me capital MA. So I've got F spring is little m plus big M times A. And then I can go back, and Priya pointed out that if I canceled those m's, I would know that A was equal to mu g. And what? Yep. So that's great, but what was I supposed to find? I was supposed to find xm. Well, if I figure this out, what's that going to give me? If I substitute all those, I'm going to get the spring force. Okay, well, what's spring force equal to? No. That's the potential energy stored in a spring. Negative kx, or we're talking magnitudes, so just kx. So if I want this to work for the whole time that my two objects are moving back and forth, okay, my big M and my little m, where's the force going to be the biggest? When x is equal to what? Well, F spring is equal to kx. Is k going to change? No. Is x going to change? Yeah, because that's the length my spring is stretched or compressed. So what's the biggest x value I'm going to have? Xm, the amplitude. Okay, so if I substitute this in and I say kxm, that's going to be the biggest value I'm going to have. Okay, that's going to be where the force is going to be at its maximum. Yes, you do. So that tells me that my xm is going to be little m plus big M mu g over k. And when you substitute all of that in, what do you get? Let's see what other people get. Okay, Gianni got the same thing. No, I think that's 200. Okay, are we all good? All right. So, as we're going through this simple harmonic motion unit, we're still going to go through a lot of the stuff that we did in chapters 1 through 8. Okay, so we talked about motion, we talked about how to find the velocity and the acceleration, and that was like chapters 1 through 4. We've just done a problem that has to do with the forces involved with springs and simple harmonic motion. We talked a little bit about that yesterday, I think, where we said that it's not a simple harmonic motion unless F or A is proportional to negative x, right? We talked about how forces fit in. So that's chapter 5 and 6. And then what are chapters 7 and 8? Energy, okay? So now we're going to talk about the energy associated with the simple harmonic oscillator. So, although a simple harmonic oscillator doesn't have to be a mass on a spring, it's a convenient way to visualize it, to think about it, and to talk about it. So if we pretend we've got a mass on a spring, what's the potential energy associated with that mass on a spring? Okay. Now, for a simple harmonic oscillator, x varies in a way that we understand and that we can model with an equation. So I could say that that potential energy is 1/2 k. And then remember, my x is xm cosine omega t plus phi, and that whole thing is squared. So again, I could say that you, oh, I hit something with my thumb. That u of x is going to be 1/2 k sine squared cosine squared omega t plus phi. Right? Oh, did we spill? Oh my goodness. Yeah, I figured somebody just knocked something over, but I was just thinking that those are in fact the least absorbent paper towels ever. Okay, we just want to make all right. Okay. So that's potential energy. What's the other kind of energy that we have? We have kinetic energy. I can still talk about, well, so what's the formula for kinetic energy? 1/2 mv squared. And if I'm still talking about my mass on a spring, then, and I'm talking about simple harmonic motion, then I have an expression for V too, right? It's negative Vm sine omega t plus V. And again, I can write this as 1/2 m Vm squared sine squared omega t plus V. But now we're going to do something crazy. Well, what's Vm equal to? No. Go back to your notes from the first or second day from this section. What is it, Sari? Well, no, I don't want the whole, I only want what the Vm is, which is the thing that comes in front of the sign, which is what? When we took the derivative, what is it? Omega xm. Okay. So I can substitute that in. So now my kinetic energy, which is also a function, not of position, of time. Oh no, did I do that? This should be u of t. Fix that. Okay, it's not u of x, it's u of t. Okay. Somebody will have to help Casey fix your notes later. Okay, so k of t then is going to be 1/2 m omega squared xm squared times sine squared omega t plus v. Okay, just substituting stuff in. But a couple slides ago, we talked about ways I could write omega, especially when I had a mass on a spring. What was that way that we could write omega? 36. Not 2 pi f. I mean, that's true, but that's not going to help me here. How else can I write omega? Radical k over m, right? So this is going to be k over m. And what's going to happen if I square both sides? What do I get? Omega squared is equal to what? Yeah. So what's k equal to? So what's this equal to? Okay. So I can write my kinetic energy as 1/2 k xm squared sine squared omega t plus phi. Now, I write it this way because xm, actually there's two reasons, but one reason is because these things are easy for me to measure. Okay? xm is the amplitude. I set that. I pull the spring down or pull the pendulum out as far as I want it to go. And I can choose that. The k is the spring constant, and that's actually something that you can measure. We'll do it probably after the AP exam. We'll see how things are going. Okay, we may do it before. So now I have an expression for k of t, and I have an expression for u of t, which means that I can figure out what the mechanical energy is, right? Because that's going to be k of t plus u of t. And it shouldn't surprise you that the kinetic energy and the potential energy change, because we've looked at all kinds of systems where kinetic energy turns into potential and potential turns into kinetic. So if we write these down, our kinetic energy was what? 1/2 k xm squared sine squared omega t plus phi. Oh, cool. That's exactly what I wanted to do, was move it over. And our u was 1/2 k xm squared cosine squared omega t plus phi. What do you notice? Yeah, but I can't. Okay, so can I factor out that omega t plus phi? No, well, I can't, because it's not really something I'm multiplying by. It's the argument of the trig function, and I can't separate those things. Yeah, I can factor out kxm squared, and then I have sine squared omega t plus phi plus cosine squared omega t plus phi. Yes, it is. Why, thank you. So this is equal to 1. Doesn't matter as long as the arguments are the same. So this tells you that the total energy of a simple harmonic oscillator is 1/2 k xm, which is the amplitude squared. Okay.
What's the amplitude squared?
xm squared. xm is the amplitude. So even though u of t, in case we have to fix your notes because I did something stupid, okay? Well, it's okay. It's just this one thing. It's not u of x, it's u of t. Okay? And there's no plus sign there. Okay. So it's u of t, not, right? So even though u and k are changing as the box on the spring moves back and forth, or as the pendulum moves, that total energy is going to be the same, and it's a function of xm, which kind of makes sense. Okay, I think we can do the next problem, which kind of puts this together. So we're going to do page 437, number 27. If somebody could read it for us real fast.
What fraction of the total energy is kinetic energy? Such energy is therefore displacement. What is half kinetic energy?
Okay, so let's take A and B here first. Okay. So we're looking at the situation where x is equal to xm over 2. Okay. And then we want to know what k over Emac is and u over Emac is, right? That's what we're looking for, is what fraction of the total energy, which is Emac, is bound up in kinetic, and what fraction is bound up in potential. Keeping in mind that I have to add those two together and they have to be equal to 1, right? So what's Emac going to be equal to? Yeah, the formula we just had, which was what? Okay, xm squared. And then since what we have is a position, it's usually easier to calculate the potential energy when we have position. Because what's my formula for potential energy when I've got a mass on a spring? 1/2 kx squared. And I know what x is. So my x is xm over 2, but remember that you have to square the whole fraction there. So that's going to give me 1/2 k xm squared over 4, or 1/8 k xm squared. Right? Okay. Which means I can find u over Emac. Yeah. And what do we get? The K's, the XM's. Yeah, we get 1/4. That's it. 1/4 of the energy is tied up in potential energy. So what fraction of the energy is going to be kinetic? 3/4. Okay, so that's A and B right there. We good? We got it? Gianni? Okay, so part C wants, so displacement means what? X. I want to find the X value. So it says at what displacement in terms of amplitude is the energy of the system half kinetic and half potential? Now we already said it's easier to figure out the potential energy, right? So I want that to be half of Emec. And my Emec is still 1/2 K xm squared. I'm going to divide that by 2. And how do I find the potential energy? How do I always find potential energy for a mass on a spring? 1/2 kx squared. So I can cancel some things here, right? You with me, Sari? Okay, so I can cancel this half and this half. I can cancel k and k. And I'm left with x squared is xm squared over 2. Okay, so what's x going to be? But don't forget the plus or minus. Okay, because remember that the spring doesn't care whether I've compressed it xm over radical 2 or stretched it by xm over radical 2. It's got the same amount of energy in there. Okay? So great, that's exactly what I wanted to get done. We will do some more problems and stuff, and we'll talk about pendula on Monday. I think we're all on track for reading and stuff, so please keep looking at the portal and following what's there. What Miss